that's British Columbia in
British
Canada.
Columbia, Canada. West Coast.
West Coast. So my name is Derek Martin. I manage our solutions architects at Blackbaud, and I'm excited for this session, real-time Sky API data integration across distributed systems, and delighted to welcome our friend Jay Bell from Trellis to present this session. Jay, I'm going to go ahead and get out of your way. I'll monitor the chat for questions. I'll come back and join you towards the end of your session as you're wrapping up and help you manage questions in the chat.
Amazing. Thanks a lot, Derek. So where's everyone calling from or watching from today? Not calling. I guess I'm technically the one calling. Where's everyone from today in the chat? Just post where you're at, and I'm curious what kind of reach we're getting here. Idaho, Winnipeg. Oh, okay. Is it started to warm up in Winnipeg yet? Saskatoon, kind of the same question. Yeah. Cool. So yeah, we're at Toronto. A lot of Canadians here. That's awesome. Toasty in Saskatoon. Amazing. Yeah, it's toasty here as well. Okay, so today we're going to be talking about real-time Sky API data integrations across distributed systems. We're not going to be talking specifically about, say, the actual integration between a system and the Sky API, but more about the concepts that you're going to be leveraging to make this kind of integration work across a distributed system. So what techniques, what processes, what libraries, what patterns do you need to use to be able to make sure that the system is operating across, a distributed architecture, and you're not losing consistency, and you're not running into any kinds of problems. So who am I? I'm the CTO and co-founder of Trellis.org. I'm a Google developer expert in Angular. Some of you may be aware of what Angular is because I believe Blackbaud's Sky add-in library is built on it. I'm sure some other things related to Blackbaud is also built in Angular. So I'm a GDE for that. I'm an NX champion. I actually just found out yesterday when I was watching one of the talks that NX is used at Blackbaud, it sounds like. So that's really awesome. I actually talked to the NX team about that the other day. I'm an open source contributor. I'm the host of the Angular Plus show. So that's the official podcast for NGConf, which is the biggest Angular conference in the world. And I'm one of the hosts of This Is Learning. So who is Trellis? Quick, not about technology, just about us. We're a revenue generation platform for change. We want to empower global collective impact, and we can help you raise up to 120% more with our unique donation augmented approach to events, auctions, and raffles. So Q&A. By all means, post questions in the chat. I have it open here on my other screen. If you want to, or wait till the end, there's going to be plenty of time. I doubt I'm going to take the whole 45 minutes talking. I tend to talk a little quick when I'm doing stuff like this. My coworker, Rebecca, is also in the chat, and she will be answering any questions that she's able to answer. She's not on the tech side like I am, so if there's any non-tech questions about Trellis, by all means, ask them there. Otherwise, she's going to help me keep track of all the tech questions related to the things we're going to talk about today. All the images here I generated with Dolly, or Dolly. I'm actually not sure how it's pronounced. So if you don't know what that is, OpenAI, ChatGPT, they also created another tool called Dolly that generates images for you based on prompts. So I had a little fun with that. And they're all drawn with crayons. So just a little something fun for this. So what process are we talking about here? We are discussing the actual real-time nature of pushing donor data into Razor's Edge via the Sky API. Now, that could be NXT or not. It doesn't matter. It's just Razor's Edge in general using the Sky API. So let's say a donor makes a checkout. The checkout hits the Trellis automated process to do all of the, the payments and the generation and all of that kind of stuff, or your process, whatever that might look like when a payment goes to be finalized. And then that data needs to be sent to RE somehow. So this is kind of the flow of data. There's some gotchas through this process, right? Because it's not quite as simple as just doing 1, 2, 3, especially once you start adding a distributed aspect to it. So what's the problem? There's a couple. We don't want access tokens. So access tokens are the authentication method that you use to authenticate the Sky API. We don't want them to be refreshed because they say they were about to expire while another process is using them. Let's say you have two servers, right? They both get triggered at the same time. Two donors make a checkout. They both go to pull the access token from your database. And then just because the timing was just right, the one thinks the token's expired, but the other one doesn't. The one goes to make a request with that token, but the other one saw it was about to expire or is expired and refreshed it. Now the token's invalid and your other server fails and gets an unauthorized error. Access tokens have an expiry of 60 minutes by default. So you want to make sure that you're only using them within that window, but also only refreshing them while another process isn't about to use it. We want to stay below the rate limits for the Sky API, and we want to manage all of our resources efficiently. So these could be, the servers and the databases, caches, other things like that we're going to talk about. So managing your architecture, make sure you're not overwhelming your architecture with tons of processing. Let's imagine one of your donors or one of your customers, so like an organization, a charity, just hits it big, and suddenly there's 200,000 checkouts happening all at the same time. Assuming your servers can also handle that, what do you do with all of that data that you want to push into RE in real time? So what's the solution? A rudimentary solution would be to ensure that only one process is able to make a call to the Sky API at a time. But what if you have an influx of payments in a short period of time, kind of like what I was just mentioning there? So let's say there's, tens or hundreds of payments coming in per minute or per second, right? Some big systems like Shopify or Amazon are going to be processing thousands, tens of thousands, hundreds of thousands of payments in a very short period of time. These all start to back up now, right? Because if you're only allowing one call to the Sky API at a time, you start to back up and back up and back up. And now you're kind of breaking that third rule of managing your resources efficiently, right? So will this work? Just doing the one at a time kind of thing, right? Maybe if you have a low enough, throughput of requests going through. But let's just break down what happens when creating a gift in real time with API calls. So with Trellis, when we talk about this, we're actually inserting the data into RE as soon as it's being created. We're not using like the batch mode of gifts. We figured out a way to automate this whole process so the charities don't actually need to go in and download an export or go through batch mode or any of that kind of stuff. So just to, get one gift from one purchaser into the system, you need to get the constituent to see if it exists. If it does exist and updates are needed, then you update it. If it does exist and updates are not needed, then you just continue to the next step. If it doesn't exist, then you create it. And then for each gift in the checkout, you have to create the gift. So these API calls start to pile up, right? If we want to do this kind of upserting functionality so that we aren't overdoing the API calls, we're not backing our servers up, right? Because this is, possibly 1, 2, 3 at minimum, maybe 1 or 2 more, 1 or 2 less, right? So now we need to scale the system, right? Let's imagine we're processing thousands of API calls a minute. Once you start to throw all of these at the system, it starts to get backed up, like I was talking about, right? We always want to be upserting, right? We don't want to be overwriting. We don't want to be creating duplicates. So the number of API calls just exponentially grows and exponentially grows over time, right? And then they get backed up and your servers might get overloaded or holding tons of things in memory. And you still need a mechanism to hold these things, right? Let's say you're doing it synchronously within your checkout process. Well, now suddenly your donor's not getting a response quick enough, right? Because the request that they made to process their payment is being held up by this call to RE. Maybe the mechanism holding them, maybe you fired it off into a asynchronous process or something like that on the same server. Maybe that process times out because it's just waiting and waiting and waiting and waiting for all these API calls to get processed. And then, of course, data can take a long time to sync depending on the load, right? If you're processing thousands of these every second or every minute, it could take a while for the data to actually end up in the system. Of course, that is still capped at your API rate limits, but we can do better than just processing these sequentially one at a time. So the way we're going to talk about today is distributing it. So let's distribute this process. One way is to ensure that to not get overloaded, we can distribute our work across a cluster or a network of servers. So say we have, we use AWS. There's a there's a data center in Montreal and there's one in Ohio, I believe, right? So we could distribute our system so there's one server in Montreal, one server in Ohio, or maybe there's 4 in each, right? Now all 8 of those servers need to communicate together. So this brings in its own host of problems. Yes, we start to begin to solve the backing up of API calls and requests and resource utilization and stuff like that. But now how do we coordinate shared resource access, right? How do we not overload our database reading and writing access tokens? And how do we control the throughput of API calls, right? Well, we can't just spin up one server per API call. Like, even if that was possible, we don't want to, because what if we have so many API calls that it's actually above the rate limits? Now we're hitting the rate limits. So what the heck's a distributed system? I kind of talked about this, right? But it's an architecture that spans multiple entities. You have all these entities in a web, and they're all connected together. You can see this lovely image generated by Dolly here. This is theoretically a distributed system of computers, all attached by crayon drawings, right? Distributed coordination. So we talked about this in the previous slide, where it's like we need some way to have our servers communicate with one another. We don't want to just spin up all these servers and have them operating in isolation and not actually knowing anything about one another. So that, because then they might access the same resource or overwrite certain data, all of that kind of stuff. So we need some kind of coordination mechanism. A coordination mechanism is something that the distributed system can use to communicate with each other, coordinate with each other, if you want to say it that way, right? So what kind of coordination mechanism are we going to talk about here? Well, one way to do this, and of course there's a million ways to solve any kind of problem in computer science, but we're going to talk about caching, queues, and locks. Caches are quick access temporary storage. Queues is an ordered collection of elements. So a queue, like you're standing in line. And a lock is a mechanism to coordinate shared resource access. So only one person can access this thing at a time because they've locked that resource. There's an extension of this called semaphores, and they're a little bit more advanced, but we're just going to discuss locks right now. So you're probably asking, like, but Jay, how do these actually help us, right? And some of you might have an idea about this, and some of you may even have used this before, or you're currently using it in your organization. Obviously, I'm not sure, but what you can do here is, so what these do is caching reduces the load on the database by offloading frequent database accesses, right? So a cache, again, is a quick access temporary storage. It doesn't technically need to be temporary, but a lot of times there's a TTL on certain entities so that they're just not held forever. But caches are way quicker to access. They're faster to respond, so they're great for like reading and writing these things that you need super, super often, rather than just like pushing database queries and select queries to, say, your SQL database, or if you use Mongo or something like that, right? Locks ensure deterministic access order for shared resources. So if I acquire a lock on something and then Rebecca wants to access that thing, she would go try to acquire a lock, but it would say, sorry, Jay currently has this locked out. You can't use it yet. And then when I release my lock, then it says, okay, Rebecca, now you can acquire the lock on this resource. And now you have it. And if Jay wants to access it again, he needs to wait until you're done. And then queues, they help throttle and distribute operations. So let's say, like, imagine you're going to renew your driver's license or something like that, right? And there's a bunch of people working there. Everybody's in the same lineup, the same queue, but every time one of the workers opens up, you can go to that worker. So why caching? I talked about how it's quick and fast and stuff like that, but here's some actual numbers. I just pulled these from the internet. The sources are at the bottom there. So from the actual Redis website, Redis is if not the most popular caching solution in the world. It's wildly popular and just built amazingly. And then also Microsoft's troubleshooting page about SQL Server. So Redis cache, its time to request and get your data back is measured in sub-milliseconds. So about like approximately 200 microseconds, but it can be as low as 30 microseconds. SQL Server, on the other hand, is between like, they say 10 to 15 milliseconds per transfer. If it's above that, they think it's a problem, but this is the kind of speed they've seen over their many years of operating SQL Server. So 75 times faster to pull, say, the access token from Redis than it is from the database. So way, 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 way faster. And if you're processing so many things, hundreds of thousands or hundreds of thousands at a time, you're going to want something that's really fast to access, and you're not just going to hammer your database. So locks, locking in a distributed system. Locks are a way of ensuring that a Sky API key, for example, or some other Razor's Edge entity can only be accessed by a single process at a time, right? Like I was talking about, if I have the lock, Rebecca can't access it, but then if I release it, Rebecca gets it, and vice versa. In a distributed system, you need to leverage something like, say, Redlock. We use Redlock here at Trellis. It's a locking mechanism built on top of Redis. So it's extremely fast to acquire and release locks. And it's a way to centralize it, right? Because you're going to have one Redis cluster, or you're going to have one Redis, server, or a cluster of Redis instances that are all being kept in sync. So all of your servers connect to the same Redis cluster, and then they know they can acquire locks through this Redlock library or some other library. It doesn't matter. It doesn't really matter what you use at all, as long as it's a locking mechanism, right? To centralize this, I have the lock, you can't access anything. Okay, now I'm actually releasing my lock. So a little bit, high level, but in practice, what you might want to lock on is, say, you want to update a constituent, right? Lock on the constituent ID so that only you can operate on it. And then anybody else that wants to operate on it needs to wait until you're finished. Or you could lock on the environment ID, right? When we connect to a Razor's Edge environment, we get an ID for that customer's environment. Maybe there's an environment level configuration that you want to operate on and do something with. You can acquire a lock on, well, with Redlock, it's just a string. And whatever that string is essentially the primary key for the lock. So you can just use the environment ID as the lock. And now suddenly only one process is able to make those environment level configurations at one time. So why should we use a queue? So, I was talking about that, the post office example, right? They allow us to control the amount of processes that are running at a time. So again, let's go back to the post office, right? You go there, there's 3 attendants that are all shipping packages out, right? But there's only one queue of people. If one attendant opens up, someone from the queue can go to that attendant, and then another one opens up and the person can go to the next one, right? But maybe one of those 3 people goes on a lunch break or server crashes, right? Now suddenly that one's not there, and it's not accepting jobs anymore. So now the queue is being processed by the 2 workers, the 2 servers. So this is a way to artificially throttle the number of processes interacting with the Sky API at one time. So the standard rate limits found on this the docs page here are 25 a second and 25,000 a day. So imagine we weren't using, or let's just say we had, for whatever reason, you have 500 servers distributed around the world, right? If you had 500 checkouts happen at the same time, you might end up processing more than 25 API calls a second, because you have enough servers to process every single job in the queue all at the same time. All of those jobs are doing making multiple API calls, getting constituents, creating GIFs, updating fields, whatever it might be. And now suddenly you're maxing the API out, right? So if we know what our rate limits are ahead of time, like we do in this case, we can configure our queues so that they only process as much as we want them to process. So putting it all together, you're probably thinking it looks something like this, where I just took a pen and just scribbling things or whatever, right? Or I have this wall full of and I'm just connecting string, okay, now this goes here, and then, just follow me over here, and then suddenly this is processing. It's actually a lot simpler than that. So the architecture. These are just random pieces of technology that I've chosen. Obviously, your database could be different, or your cache layer could be different. You could be using Memcache or Redis or whatever, Postgres or MySQL. It does not matter. These are just icons to represent the actual, the concept of sorts there. So the public API adds a job to the queue. The public API in our case would be our servers processing a donor checkout, right? That would then add a job to the queue and say, okay, checkout XYZ needs to have its data processed to push into Razor's Edge. The queue would then trigger the job on one of the workers, right? One of the servers that's set up to listen to this queue to process jobs. The workers pull from the cache. They would just be like, okay, well, I need to do this thing, so I'm going to go pull the access token from the cache. Oh, it's not there. Okay, I'll pull it from the database instead first, and then I'll write it back to the cache so that subsequent calls can be quicker. And then, of course, there's going to be some additional validation, like, they're going to acquire a lock on the access token so that only they can use it at this one time for this environment, right? We don't want to stop, like, Charity XYZ's API calls just because Charity ABC's API calls are going, right? So these are kind of, they're separated. So we're going to acquire a lock on this environment's access token, check to see if it's valid or not. If it's not valid, then we would, refresh it within this lock so that we don't mess up any other requests, and then continue on with our processing. And then after that's all done, the worker will release the lock, and then now we can continue processing and we're good to go. The next job in the queue can be pushed to the workers, or maybe like multiple workers are processing jobs across multiple environments at the same time. It really depends on how you set up. Like, realistically, if you wanted to, you could have like one worker per environment, and then you could just always be that worker's dedicated to that. But then you might end up with idle workers while one's overloaded because one charity is processing more than another, and et cetera, et cetera. So what does this help with? All of this together helps with preventing duplicates, managing rate limits, optimizing resource utilization, and ensuring data consistency. So preventing duplicates. The locks are the biggest part of this. If two checkouts come in, right, and we need to create a constituent for them, we don't want to create the constituent twice. We want to upsert the constituent, see if it exists, and then update or create. Managing rate limits, right? We just talked about this. Artificially limit the amount of jobs that can be processed in your queue so that we don't go over this rate limit. The queues can only process so many. Optimizing resource utilization, very similar to the queue and the rate limit one, is we don't want to process every single job at the same time, because you might have so many of them that you bog your servers down, and then maybe they run out of memory, or they spike their CPU, and now suddenly other operations aren't working and stuff like that. And then ensuring data consistency. So, operations should theoretically be in a FIFO order, first in, first out order, right? So if we have multiple servers operating on the same entity in Razor's Edge, gift or constituent or, participant or participant donation, whatever it might be, we don't want servers like continually overwriting one another, right? One server says, okay, I need to create it and set these values. Okay, I'm going to do that. And then while that's happening, another server might be waiting to see when they can do that, and then make sure that their data is consistent, because their process happened afterwards. So their process, whatever it's going to do, should be the resulting state of whatever that entity is. Without locks, we would possibly have a situation where each process is processing its API calls over top of one another, and then suddenly you're not consistent anymore. So I kind of just actually talked about this, duplicates and data consistency. So when you're making your gets and your posts and your puts, you might want to consider locking on that resource itself, like that entity's resource ID. Rate limits and utilization, right? So usually with queues, you can configure, say, a global rate limit for the entire queue, and that queue would be based on the the database that's backing it. So we use a queue that's backed by Redis, so it's really fast, right? We say for this queue, only so many jobs can be processed at a time. But there's also going to be a configuration to limit the number of jobs per worker. And you can tweak these and configure them so that you are under the rate limits, but as well as not overloading your servers, so you're not just destroying your resources and not you're over processing. Helps evenly distribute all of this work over your cluster of servers. So wrapping it all up, concepts we learned about. Using queues for deterministic processing, right? Queues are typically, and I believe this is configurable depending on what library you're working on. They're FIFO order as well, so first in, first out. If a job's added first, that job should be processed first. Just like, you're not budging in line at the post office, right? If I show up first, Rebecca's not allowed to go in front of me. Using locked for consistency. I'm not allowed to operate on entities that are currently being operated on, right? Pretty simple. And then using caching for performance. Why would I, walk over there and pull this data from something that's going to take longer to get if I could walk over here and pull that data from something that's really fast to get, right? And then if that doesn't exist there, then I can go over to the slow one and then put it in the fast one so that future people, myself included, can access it quicker. That is it. That is the real-time data integration with the Sky API. I know that was a lot of content to talk about. I tend to talk quickly when I do these kinds of things, and I know pretty well, so hopefully it was clear enough. And if it wasn't clear enough, please ask so that I can go back to the right slide and we can dig a little deeper into it. Like I said, we didn't cover specifically the Sky API integration. It's more about the concepts and the processes you need to operate at scale. So hopefully I got the point across. Distribute things and cache things. Thank you, everyone.
Thanks, Jay. Very informative. You did move quickly through these, through this. Folks, we do have a few more minutes left. If there are questions for Jay, let's get them in the chat.
Yeah, be happy to answer them. I didn't see any pop up during, so maybe everyone's just really smart here and they're all like, oh, Jay, I already know all this stuff.
Is this AI generated art here as well, Jay?
Yeah, every image in here, except for the architecture one, I used a library for that, but all the images were generated by Dolly, yeah.
It'll be great when it learns how to spell.
I know, there are some pretty bad ones.
Okay, well, we won't hold on to folks and we won't hold on to Jay. If there are no questions for him, folks, there is a session survey that we ask attendees to complete after every session. Let me just grab that link and put that in the chat so that folks have access to that. But that's important so that we can plan for future events and also
right,
so that you can win. That's right, so that Jay can win and get to BBCon and all of that good stuff. So I just dropped that link in the chat. Please do take the time to complete that survey for this session. And I hope everyone's had a great BB Dev Days day today. And thank you.
Awesome. Thanks a lot. Bye, everyone.
Okay.